Finally. Finally. Testando. 1, 2, 3.
Eu vou conferir como é que está esse stream.
Tá. Se você está no site do PESC, vai estar lá. Testando. 1, 2, 3. Okay. I think we're all set. Sorry for the long delay. Ok. Pessoal, bom dia a todos. Sejam bem-vindos. Desculpa aí o atraso com os problemas técnicos. É a primeira vez que a gente está usando essa sala para fazer isso, mas conseguimos resolver tudo, ok? I'm going to switch to English to introduce Professor Vazirani. So it's really a pleasure to have you here today with us. Professor Vazirani is a professor at the University of California, Irvine. He's a distinguished professor there. He finished his PhD at MIT.
Undergraduate at MIT, PhD project.
Good. Undergraduate at MIT and his PhD at Berkeley. And he works in the area of algorithms, in particular, more recently, algorithms for markets, mixing game theory, economic theory, and algorithms. And I think that's the topic of the talk today. He's the co-author of Approximation Algorithms, a very influential book. I think 20 years ago, the book was published, maybe 25 years ago by now.
20 years ago.
20 years ago. And he's in Rio participating in a workshop at ICLR, which was 2 days ago. And he took the time to come visit us at UFRJ and give us this talk. It's his first time here at UFRJ, not in Rio. He told me he was here about 20 years ago. So a bunch has changed since then. When we drove here today, we were able to see some of that. So he's going to be here for the talk. We're going to have lunch after, and he's going to be here in the afternoon. So if you want to talk with him and discuss with him your research, he's very open into that. So you're welcome to join us afterwards. So thanks again for visiting us and for taking the time to give us this talk. It's really a pleasure to have you here.
Thank you.
It's all yours.
Thank you. So, yeah, it's a pleasure to come here. Always a pleasure to visit you, wonderful city. And thank you for coming. So, I'm going to talk, my talk is about mechanism design. And in mechanism design, there are two key requirements for a good mechanism. One is that it should have good game-theoretic properties. And the second is that it should have computational efficiency, obviously, right? And a poster child in this respect has been the Gale Shapley deferred acceptance mechanism for stable matching. It is efficiently computable, the stable matching. This was work done by Gale and Shapley even before the definition of polynomial time came about, and it's a polynomial time algorithm. And it gives a solution which is in the core of the game, which means that it enforces stability. People don't want to secede from the stable matching found. And it is incentive compatible to the proposing side. Am I loud enough, or you want me to be louder? Okay. So it is incentive compatible from the proposing side, and that's very important for applications. And there were lots of applications matching residents to hospitals or students to schools and so on. So many that and Al Roth was responsible for many of these applications. And Gale had already passed away, and in 2012, Roth and Shapley got the Nobel Prize in Economics for this work. So that's the importance of designing mechanisms that are both computationally efficient and have good game-theoretic properties. What I'm going to talk about today, okay, so this particular stable matching work is based on ordinal preferences. So if you're matching workers to firms, each worker has a complete preference list over the firms, and each firm has a complete preference list over the workers. And in this talk, I will switch to another way of expressing preferences, which is the ordinal preferences. And I'm going to talk about one-sided matching market, where you have agents who have preferences and, let's say, indivisible goods, not strictly indivisible goods. Something to be adjusted here. What is this for?
This is your video. You're too close to the camera. He's telling. We'll put the camera here.
So the goods are indivisible. That's important to note. And the agents have cardinal utilities, like this. Say this person values this house to the extent of 1, 2.5, and 4. So this is better than this is better than this. And so if I take these cardinal utilities, I can also convert it to ordinal, just by saying that the preference order is this better than this for this person. But notice that if I replace this 4 by 100, I still get the same preference order. This is better than this, better than this. But a lot of information has been lost because this person really prefers this house, the third house. And that's the difference between cardinal and ordinal utilities. Cardinal are more expressive, and you get significant gain in efficiency. And there were results showing that every agent improves by a factor of theta log n, going from ordinal to cardinal. On the other hand, ordinal utilities are easier to elicit, and the mechanisms are well developed. What about mechanisms for cardinal utilities? So the main story is that recent computer science insights put this whole thing in a state of flux. Cardinal utility mechanisms. But new results may have led to a resolution. And that's the whole story. I'll show you in what sense were there computer science insights that put this whole business of designing mechanisms for cardinal utilities in a state of flux. What kind of a flux did it get into? What was the big mess that happened? And how did we get out of that mess? We are still trying to get out of that mess more and more, but to some extent, we already came out of that mess. And I'll show you all of that. Okay, so that's the outline of my topic, of my talk. Any questions on that? Are we all right? And I'm audible, right? Or should I scream a bit more? Oh, okay. So, what I'm going to talk about is a Hylland and Zeckhauser mechanism for this one-sided matching market, where you have preferences on one side which are given by cardinal utilities. And what you need to find is you're given n agents and n indivisible goods, and you have to find a perfect matching between them, which achieves desirable game-theoretic properties. Now, the first question that arises is which properties? Okay, so first of all, you should have Pareto efficiency, which means that the allocation should be such that you cannot improve anybody without decreasing somebody else, hurting somebody else. So it's maximally good. And this is easy to achieve by itself, such as order all the agents in linear order and let them pick their most desirable good. Nobody will do worse than whatever they can get currently, and hence nobody can be improved without hurting somebody else. Okay. But the problem is that Pareto optimality by itself is not meaningful, and this particular way of just ordering arbitrarily is not good. And the reason it's not meaningful is that you can give the best objects to one person, but that doesn't mean that people are not going to be envious of that person, right? So what I want to say is that it's not meaningful by itself. You have to have fairness of some kind, namely envy-freeness. Okay. What does envy-freeness mean? It means that no agent prefers another's allocation to their own. You at least want to ensure that together with Pareto optimality. Now, as I said, in our market, goods are indivisible, and for indivisible goods, there's no way to get envy-freeness. For instance, even if you have two goods and two people, one very good good and one not very good good. Okay, everybody wants, both people want this good. So no matter how you allocate, one person will be envious of the other. So should we just give up? Well, there are some alternatives to complete NV-freeness, such as NV-free up to one good, which is a very nice solution concept, award-winning also. But it does not apply here because everybody wants only one good. So NV-free up to one good makes no sense. So how should we proceed? Or how did Hylland and Zeckhauser proceed? That's what I want to show you. But I also want to say that one more requirement would be incentive compatibility, which means that revealing your true utilities should be your dominant, should be the dominant strategy. You should not, cheating should not help you. Okay. And Hylland and Zeckhauser gave a pricing mechanism inspired by general equilibrium theory, which gives these nice properties in the following way. Okay, so what's the pricing mechanism, first of all? How many people know general equilibrium theory? Not really. Yeah? You do, right?
I'm not sure if you in the depth that we need, but I know fingertips.
Good, yeah. It's good to have somebody who knows
Fingertips.
So, what is the pricing mechanism? It's a mechanism that creates parity between supply and demand. Okay, and for instance, in the West, we have a free market economy, more or less, and that tries to create parity between supply and demand, and that has many nice properties. These are called equilibrium prices, where supply meets demand. The nice properties include the fact that they achieve stability in prices. The prices don't keep just going up and down. They achieve efficiency in the marketplace. For instance, the Soviet Union collapsed because it wasn't because the prices were being decided by some central authority in some crazy manner, and which was not good for the economy as such. So, and also we know the prosperity that the free market economy brought to the West, right? So the big question in economics was, do such prices even exist where you have parity between supply and demand? And this was studied under general equilibrium theory for a century and a half. And they gave many, many market models in which they established the existence of such equilibrium prices. Just to give you a sense of what equilibrium would be, let's see in the case of one good. If you just have one good, you have supply and demand curves, and wherever they intersect, it's equilibrium price. And if you lower the price, then demand exceeds supply. If you raise the price, then supply exceeds demand, and you won't have equilibrium. And so the only place that you will stabilize is at equilibrium prices. But this is too easy. In a normal market, you have many, many buyers with many different buying power and many, many goods, and people have all kinds of different utility functions for these goods. So does equilibrium exist in a usual complex market? And this was a very big theorem of Arrow and W showing the existence of such an equilibrium using the Kaplan fixed point theorem, which is the deep theorem in topology. And of course, you know, both of them got Nobel Prizes as well. So, Hylland and Zeckhauser applied the pricing mechanism to this one-sided matching market, but this market is fundamentally different from the market studied in general equilibrium theory, in the sense that this market has no money and goods are indivisible. But in general equilibrium theory, money is intrinsic to the model and goods are divisible. It's very important that the goods are divisible there. So what do Hylland and Zeckhauser do? First of all, they make goods divisible, infinitely divisible. They assume that each unit of good is one unit of probability shares. And those probability shares can be divided in any, they are like fluid. You can divide it among the agents in any way you want. Okay. And you assume that every agent has $1 of fake money. Remember, the model had no money. We'll artificially put in money, $1 of fake money for each agent. And we'll, so the utilities are cardinal. Uij is the utility of buyer F for good J. And we'll have price variables Pj, which are determined by supply and demand considerations, and we'll find an equilibrium prices and allocations so that each agent gets 1 unit of probability shares, maximizing her total expected utility and costing at most $1. Okay? And all goods are sold. That's the equilibrium. So everybody gets an optimal bundle, which means an optimal utility maximizing probability shares of exactly 1 unit and costing at most $1. And all of that can be obtained by solving an LP once you know prices. You can solve, I'll show you what kind of an LP it will be. And all the goods need to be sold. Okay? And this allocation, because see, everybody gets 1 unit of probability shares, and every good is 1 unit of probability shares. So, and we have n goods and n agents. So what we'll get at the end of the day, an allocation which is a fractional perfect matching. It will add up to 1 on this side and 1 on this side. Okay. And once we get a fractional perfect matching, of course, in our original problem, the goods are indivisible, so we have to do rounding. And for that, we apply the famous Prof theorem to round the fractional perfect matching to an integral matching and be done. Okay. So, I promised you this LP, and this is the LP for obtaining the optimal bundle for agent I at prices P. So Xij is the probability share of good J allocated to I. And so this is the expected utility of I, because this is the probability share, this is the utility from 1 unit of probability shares. Okay. And there are 2 kinds of constraints, size constraints saying that the optimal bundle should be exactly 1 unit of probability shares, and the cost of that bundle should be less than equal to $1. It could be strictly less also, but not more, because the agent has only $1. They can have unspent money. For instance, if they cannot buy more, you cannot exceed the size constraint, so you just buy less than $1 worth of good. Okay, so that's the LP that gives you an optimal bundle.
Sorry,
yes,
what
sir.
about the preference?
The references are here, UIJs, the utility.
So that's given.
Yeah, UIJ was given, right?
You're solving for Xij.
Yeah, you're solving for Xij. Yeah.
And what about PJ? You're also solving for PJ?
PJ is given. You assume that you have PJ, then this LP will give you so at prices P, this LP will give you the optimal bundle. But of course, the full problem is to find the correct PJs and the correct Xijs so that the whole thing works out. It's a hell of a lot of conditions. Everybody should get an optimal bundle. The market should clear exactly. And that's why equilibrium computation is such a difficult task.
Okay. So if you have the prices, this would be the.
Yeah, but you still have to find, you have to find the prices and the look. It's a little bit of a chicken and egg problem also. But if you don't have the prices, you don't get allocations. You don't know. I mean, it's a tough problem. You have to go round and round in circles to get it. Yes, somebody has a question here.
How can we ensure that everybody is being honest?
So you're talking about incentive compatibility.
Yes, because under this formulation, like let's suppose we have 3 houses. One a very good house, one house that is almost as good as the first one, and a very bad house. And then if I was being honest, I would say, okay, this is great, this is also good, and this is terrible. But I can just say I only want the first house, 100% in the first house, and ensure that I get the best.
I'll answer the question towards the end. Okay. So how to bring incentive compatibility into this mechanism? Okay. That's a very good question. But let's see what properties Hylland and Zeckhauser satisfies. First of all, they show that equilibrium exists using Cardinal-Utility theorem. And the properties are Pareto optimality, that comes from first welfare theorem. NP freeness ex ante, before you round. So the fractional perfect matching is NP free. Nobody envies somebody else's fractional perfect matching. After you do the rounding, of course, the bets are off, because whatever you get when you're going from fractional to integral. And to answer your question here, it's not completely incentive compatible, but it's incentive compatible in the large. That means if you have a very large market with many agents of the same type, many goods of the same type, then nobody gains by cheating. But I don't know what exactly that means. and you cannot get full strategy proofness here. Okay, but even this will be able to repair. This is a weakness here of Hylland and Zeckhauser, but we'll be able to repair this to some extent, and when we come back towards the end of this talk. Okay. So, what about computational efficiency? That's the other requirement, right? Game-theoretic properties is just one of the requirements, and that we achieved through the pricing mechanism, which is already quite a big idea to use the pricing mechanism for this one-sided matching market with indivisible goods. Okay, such a big idea that economists really swear by this mechanism. They love this equilibrium-based mechanism, and it's very, very famous. It was given in 1979, as you can see, way back. But what about computational efficiency? Now, the economists, if you ask them, they will say, okay, people will. It's reasonable that they will find a good solution by just trading, and this goes under the fancy way of saying it. The invisible hand of the market will find this equilibrium. The Adam Smith's invisible hand of the market. Whether it will or will not is still, just by saying it, you don't just get efficiency, right? You still have to prove it. And in the study of market equilibrium in algorithmic game theory, we have realized that many markets simply are not efficiently addressable through the equilibrium finding problem is actually computationally hard. So on the other hand, for computer scientists, this mechanism was a marriage between a linear Fisher market and fractional perfect matching. And I'm going to introduce to you the linear Fisher market, but I want to say that fractional perfect matching is in polynomial time. Linear Fisher market is also polynomial time. So many people thought that this marriage between two polynomial time algorithms, combinatorial algorithms, should lead to a combinatorial polynomial time algorithm. And I must say I was in the same boat. Okay, until all hell broke loose, so to say. So let me go further into that story. So I want to introduce to you the linear Fisher market, by just saying how it is different from Hylland and Zeckhauser, because there's just a couple of small differences, but it makes all the difference. So in linear Fisher market, goods are divisible, like in all market equilibrium models. In matching markets, goods are indivisible. Here, goods are divisible. And there's no size restriction on the agent's optimal bundle. Whereas in matching markets, each agent should get 1 unit of probability shares. And agents have arbitrary amount of money, MI, not just 1 unit, but that's not a big deal. 1 unit is just as easy or hard as arbitrary amount of money. So what happens in a linear Fisher market to that LP that I introduced for computing the optimal bundle, you still want to maximize the utility of the agent. Xij is the amount of group J allocated to agent I. So that's maximizing the utility of agent I. This constraint goes away because there's no size constraint, as I said. And the money does not have to be $1, it's MI dollars specified as part of the input. So that's how you calculate the optimal bundle for each agent I. A little bit different, right? But that makes all the difference. And this is polynomial time computable. And so equilibrium, of course, means that supply should equal to demand. But why is equilibrium computable here fast for this linear Fisher market? That's the question that arises. Okay. And the reason is that the linear Fisher market satisfies a very important economic property called cross substitutability, which says that increasing the price of one good, the demand of another good cannot come down. Okay, which is saying that there's no complementarities between the goods. So suppose there's complementarities between the goods. So suppose you take two goods that are complements, like bread and butter. If I increase the price of butter, the demand of bread will go down because people buy less butter and hence buy less bread or other way around. Okay, so without complementarities, V cross is possible. Okay, and it holds a linear fissure, and this is central to the polynomial time algorithm. On the other hand, for Hylland and Zeckhauser, V cross does not hold because there is a cost constraint as well as a size constraint. Remember, that's the big difference between Hylland, Zeckhauser, and linear fissure. That there's also a size constraint here, and they clash. I'll show you how. Okay, through an example, I'll show you how they clash, and this is the main hurdle in obtaining an efficient algorithm, that you don't have V cross substitutability. Do you want to see this complex example, or should I just move on into the talk?
No, the example I think is good.
Okay. So here's the example. Suppose agent I likes two goods, G1 and G2, and G1 is a very very useful but expensive good. So the utility obtained from 1 unit of G1 is 100 million, and the price is $1 million. But the agent, of course, has only $1, right? And wants to get 1 unit of goods. So she can get only 1 in a million amount of this good at most for that $1. But she still has to, 1 in a million will just not fill her bin at all. Tiny amount will be filled, but she needs to get a full unit of good. And so fortunately, there's another good which is I call cheap fluff, because it gives epsilon utility per unit and has price epsilon per unit. And so her optimal bundle will be to get just an epsilon amount of good sorry? The other way around, yeah. How did that happen? Yeah, good point. You're following it at least. So G1 she will get just epsilon, and G2 she'll get 1 minus epsilon. I don't know how that happened. No, never happened. Maybe on the flight it got changed. Because it never happened in the previous talks. It happens on the way to Rio sometimes.
I don't know.
So
The weather.
Yeah.
Changing.
maybe it went for a swim. Okay. Now suppose we increase the price of G2 to 2 epsilon, then what happens? Then you still want to spend 1 minus 2 epsilon on G2, and on G1 you want to spend 2 epsilon. So the price of G2 went up, but its demand went down. Right? And we said V cross substitute means that if the price of good goes up, good 2 goes up, the demand of good 1 cannot go down, but here it goes down. It goes down from 1 minus epsilon to 1 minus 2 epsilon. Right? So the price of the cheaper good went up, the demand of the more expensive good went down. Okay, so you have no V cross substitutability. I hope that's clear enough, right? I will maybe on the flight back it will all come back to normal. Oh, I'm going to solve all also. Okay, so amazingly enough, ever since '79, nobody studied the computational complexity of Hylland and Zeckhauser. I find it hard to believe, even though algorithmic game theory had been around for basically almost 20 years. And a few years ago, Mihalis Yanakakis and I started studying it, and the first thing we did was that we found an instance which has only irrational equilibria. You have to use irrational numbers to write down the equilibrium, the prices and the allocations. And as a result, this problem is not even in the class PPAD. And PPAD and FixP are analogs of NP for total search problems with either rational or algebraic solutions. So in PPAD, the solution has to be rational. In FixP, it has to be algebraic. Okay, and these are analogs of NP for total search problems. NP problems are not total. The answer can be yes or no, and deciding between yes and no is already intractable. here, because the answer is always yes, so you cannot say, oh, can we do the decision problem? No, the answer is always yes, so you can predict the answer easily. But actually finding the solution is hard, and how do you prove it? Through these very fantastic process, EPAD and fixed P. Okay, and so what we showed is that equilibrium computation is in 6P. As a corollary, we get that it can be expressed through algebraic numbers. And approximate H3 is in the class PPAD, even though exact H3 is not. You know that next to each irrational number close enough, there is or arbitrarily close, there is a rational number. So we can certainly approximate equilibrium can be expressed as rational numbers. And it's in PPAD. And we conjecture hardness for both of these. Of these, the second was resolved by Yanakakis and 3 people from Colombia. And the first still remains an open problem. So Daniel Sudok wanted me to underline the open problem. So this is certainly an open problem. Show that HZ equilibrium is fixed P hard. Okay, so what about in practice? So in theory, this is the state of affairs. Now, as a result of this work and this work, computing even an approximate HZ equilibrium is PPAD complete. So it's intractable in theory. What about in practice? Sometimes in practice things work out, right? Depends. In this case, it really doesn't work out because there's no mathematical formulation that captures the equilibrium. There's no LCP, there's no convex program, there's no non-convex program, nothing. So it's not like you could take a mathematical object and start playing with it. No. And the only way to compute it is algebraic cell decomposition, and that requires exploration of n to the phi n square cells for a size n by n problem. And for n equal to phi, that's 10 to the 100 cells. That's that many cells. And then running time is even more because, so algebraic cell decomposition, you can think of it as an exhaustive search over a small domain. But it's not very small. You know how big that number is? 10 to the 80?
The number of atoms in the observable universe.
Yeah, it's more than the number of atoms in the observable universe. So you cannot even compute it for n equal to 5, maybe not even for 4, I don't think. Maybe for 2 you can compute it, yes. So that's not much of a market. Huh? I just want to say that this is not a new phenomenon. Every intractable problem eventually reaches this number, but for large n, like 100 or 1,000, depending on different problems. But this is the first time I'm seeing this large number for n equal to 5. So it's highly intractable in practice. You simply cannot do anything. And there's no approximation algorithm known either for computing an approximate equilibrium quickly. So we have to look for alternative mechanisms. And why? Because there are numerous new applications that are coming up on matching markets in all realms of life. Whether it's vacation rentals, ride-hailing, food delivery, freelancing, many matching markets have been designed even for, of course, ad allocation, so on and so forth. And a lot of these are talked about in this co-edited book, which came out a couple of years ago. It's available on my website for free. You can download a free PDF, and you can read it or not, that's up to you guys. At least you can download a free PDF. Okay, so we change gears and see how to repair the situation. As I told you, there was a big fiasco, but there's some good news also. So let me say what the good news is. So I'm going to introduce to you what's called the Nash bargaining game. So assume there are 2 agents, 1 and 2, and she has a house on the beach, and he has a house in the mountains. That's the utility she gets by staying in her house for the whole year on the beach, and this is utility he gets by staying in his house in the mountains for the whole year. And then they get together and decide to share their houses. So she says, okay, you can take for these weeks my beach home, and I'll take your mountain home, and so on and so forth. And one way of sharing is that she gets both houses for both the entire year. He goes and I don't know, lives on the payment, and so she gets a lot of utility. Oh, so every number here, every point here is 2 coordinates. The x-axis is the utility she gets, y-axis is the utility he gets. So at this point, she gets a huge amount of utility because she got both houses and he got nothing. And here, he got both houses, she got nothing. And these are all the possible feasible points for the feasible set. And we'll assume it's convex and compact. Okay. And so these are the various ways of sharing houses. What's a good bargaining point? That's the question that Nash asked. And this point is called the disagreement point, because you don't want to go, she doesn't want to go to the left of this, and he doesn't want to go to the bottom, below this. They both want to remain in this particular region so that they are better than the status quo utility. Okay, so which is the right solution here in this status quo, better than status quo, okay, where both of them would be acceptable to the solution. And in what sense are they agreeable to the solution? So Nash gave 4 very natural axioms. The first one is Pareto optimality. So you don't want to be, you want to be on the frontier. You want to be maximally good. You cannot improve somebody without making somebody else worse off. Right? So that's Pareto optimality. And 3 other axioms he gave. I don't want to go into those, but he was a great mathematician, also Nash. And so we are a very clean, simple proof. He showed that there's a unique solution satisfying all 4 axioms, and it's the one that maximizes Vi minus Ci. Ci is the disagreement utility. Vi is the variable which ranges over the feasible set S. Okay. And this function is log concave, and because it's log concave, we take its log and we get a convex program because we are maximizing. After taking the log, we get a concave function. We are maximizing a concave function over a convex region because this S is a convex region. And so the solution is given by a convex program. And convex programs can be solved efficiently. You know that, right?
Sorry, what's the objective function? We're summing both utilities.
It's the product of the Vi minus Ci. Vi are the variables for each agent, how much utility they got, and Ci is the disagreement utility. Okay. So Vi should be ranging in this region. So V1, V2, V1 should be V1 should be to the right of this line. V2 should be to the above this line. So for instance, you can have a point here. This is V1, this is V2. Now I'm going to assume V1 and V2 are variables and maximize this product, Vi minus Ci. Okay. So that's the convex program, and so at least this is a polynomial time computable function. No intractability here. So here is the Nash bargaining based alternative for one-sided matching market. Okay, this idea can be extended into a solution for Hylland and Zeckhauser's one-sided matching market in this way, where the constraint here is that you have a fractional perfect matching. Because the sum of the xi's at each j and I add up to 1, and you're maximizing this log of this some of the logs of the utilities. So we're going to solve it as if it were a Nash bargaining point problem over this convex domain, and this is polynomial time computable. So instead of the pricing based mechanism, if you use Nash bargaining based mechanism, we get huge advantage computationally. Okay, so we implemented with Hosseini, we implemented this via Frank Wolf and Betty Plains, and managed to solve for n equal to 20,000 in 1 hour on a laptop. Okay. And you saw how intractable Hylland and Zeckhauser was. And the split markets of Procosia. Have you heard of those? He has some matching markets. For instance, assigning a bunch of friends want to rent a house, and they want to know who should get which room in the house. So they have a matching market for that. Okay. They pay different amounts each. And many hundreds of people have used this kind of facility to match these students to appropriate rooms. And it's also New York Times also does it, and they wrote an article on this split market. And there are many other markets also. Okay, so this is fine, but the question is, seems to be pulled out of the hat, right? Instead of this pricing mechanism, we suddenly switch to Nash bargaining. How? Where did this idea come from? Right, that's the question. So let me say a little bit about that, and then show you more applications of this same idea beyond one-sided matching markets. Yes, sir.
So by changing the bargaining solution, you remove the price and it was multiplying the excitation as a source of non-convexity.
Mm-hmm.
Because you can state the summation of Pij excited
Equal to, yeah.
So you're removing the P.
There's no prices left anymore.
There's no prices left.
Yeah. There's no money either.
There's no money. Right.
Yeah. So we're just using the pure form of the original problem, which is given utilities and nothing else. And we just want to find these excited. There's no prices. Of course, these will have dual variables which can be viewed as prices, but they're not prices in the original sense. Okay. So, where does this idea come from? So, what's the relationship between pricing and Nash bargaining? Best to look at it in a very simple setting of linear Fisher market, which I introduced to you, and solve the linear Fisher market as if it were a market or as if it were a Nash bargaining problem, which means that you want to goods and utilities, and you want to so whatever works for two agents in the Nash bargaining also works for n agents, and again you want to maximize the product of utility minus. Okay, so both these mechanisms, whether it's the pricing or the Nash bargaining, give the same solution for linear Fisher market, and the underlying reason is that the linear Fisher market equilibrium is captured by a very classic convex program due to Eisenberg and Gale. And it's quite a fantastic convex program, as we'll see in a moment. It has many very attractive properties. And the same convex program actually captures the Nash bargaining solution for the same allocation problem. Okay. And why is it? Okay, here's the Eisenberg convex program. And the KTT conditions, when you apply KTT conditions, you get equivalent allocations and prices. The prices are the dual variables to these constraints, saying that everybody gets that the total amount of each good available is 1 unit, right? There's only 1 unit of, but without loss of generality, we assume that the market has exactly 1 unit of each good by redefining what that unit means. So no matter how much rice there is in the market, I'll call it 1 unit and start dividing it. No matter how much oil there is, I'll call it 1 unit. Okay. So these dual variables for these constraints will give us equilibrium prices, and these excited optimality will give us allocations, and that's the Eisenberg-Gale convex program. Okay. Now, how do we write out?
Sorry, Vijay, can you go back one slide? One.
More?
I'm puzzled here because the linear Fisher model, you need the prices, right?
Yeah, so these come out of the dual variables to these constraints.
But it's a parameter of the model, right?
No,
in the linear Fisher market.
No. You have to find prices and allocations. So
Okay.
the primal finds you the allocations, the dual finds you the prices.
Okay. You have to also find the price.
Yeah, you also have to find the prices. And the dual gives it to you.
Okay. That's why it's equivalent.
Yeah.
And that the equivalence comes from finding the prices in the Fisher market.
Right. The entire Fisher market is solved by this Eisenberg-Gale convex program. And similarly, if you want to solve this using Nash bargaining, you will of course do this, as I said. You will maximize this concave function subject to the convex domain. But if we move from the utility space to the allocation space, we will replace VI by the utility obtained from the allocation, right, by this sum. And we will replace this by this, the VI here by this. And we move from VI in the, which is a space in the, we can write it in the allocation space as if the total amount of good, each good being sold is 1 unit. So we obtain the exact same convex program for Nash bargaining way of solving this same allocation problem of linear Fisher. Okay, so at linear Fisher, both these coincide, pricing and Nash bargaining. And this is something that I observed a long time ago. And I will also come to other properties of the Eisenberg-Gale convex program. But for a very long time, I couldn't reconcile with the fact that such amazing things were happening all at once. And I decided that, here is another aspect, that we can obtain all n bundles via a single program. So remember, in linear Fisher, each agent, given prices, each agent had to solve their own LP. Here, you don't have to solve any LP, just this one convex program will give you the allocation for each agent, as well as the prices from the dual. Okay, amazing, right? Simply amazing, mind-boggling. And it always has a rational solution. So how can a nonlinear convex program always have a rational solution? It's behaving like a linear program, right? So, I mean, there was so much going on that I couldn't reconcile with this. And so, and this is what, and so I said, okay, can we generalize this phenomenon? So at linear Fisher market, both these coincided. Can we go to the next level of market beyond linear Fisher? What's the more general model? Turns out it's the linear arrow W market model. It's called the exchange model. I won't go into definitions because I'll be only defining too many models and you'll get very upset at me. So let's not go there. But the point is that when you go to the next level of market, pricing and Nash bargaining give different allocations. Okay. And the convex program for Nash bargaining allocation is still rational. It is still rational. Okay. And using this fact, I have managed to get an efficient combinatorial algorithm for this. And then I also defined the notion of a rational convex program, which is any nonlinear convex program which always has a rational solution if all parameters are rational. In the sense, so in some sense, it's a nonlinear convex program that behaves like a linear program. And this is analogous to another phenomenon in combinatorial optimization, where we have linear programming relaxations that always behave like integer programs. You must have come across some of those for matching, flow, shortest path, branching, and so on. Many fundamental problems in combinatorial optimization because of total unimodularity. But here, because of some other reason altogether. So, but inspired by that amazing phenomenon, I gave this notion, and then many people found these rational convex programs for many market models, and then were led to combinatorial polynomial time algorithms for them. Okay. So we go back to one-sided matching market. So remember, this slide I already showed you. So that's for one-sided matching market. How about game-theoretic properties of this? Right? How far are we doing until time?
Okay.
Any questions before I show you the game-theoretic properties of this new mechanism? So the Nash bargaining mechanism is a Pareto optimal because that's one of the axioms of Nash, but it's not envy-free. Okay? And I'll show you a simple example to show it's not envy-free. So I'm fine. But as we already argued, Pareto optimality without envy-freeness is meaningless because if you give all the nice goods to one person, you have Pareto optimality, but everybody will be envying this person. You have to have envy-freeness as well as Pareto optimality in your mechanism. And here's a counterexample to envy-freeness for the Nash bargaining allocation. So agent 1 and 2 both like good 1, but agent 2 also halfway likes good 2. And the Nash bargaining solution is to give them good 1 and good 2 respectively, because even if you give a little bit of an epsilon amount of good 1 to agent 2, the Nash product will be smaller than 1. Here the Nash product is 1. 1 times 1 is 1. But here you'll have 1 minus epsilon times 1 plus epsilon, which is 1 minus epsilon squared. So the Nash product went down. So buyer 2 should not get any of good 1, even though she wants good 1. Okay. Buyer 2 envies buyer 1 by a factor of 2. Okay, because her allocation is factor 2 worse than it would have been if she got good 1. Okay. And what we managed to show is that this is the worst example. So factor 2 is the worst example. And moreover, of course, if we don't have envy-freeness, we don't have incentive compatibility. Because if the mechanism gives us a solution where buyer 2 envies buyer 1, then she would be forced to lie and make her utilities be that of buyer 1, right? So as to get buyer 1's allocation. So in incentive compatibility counterexample, I do cheats because she really wants good 1. The mechanism is giving her good 2. She says cheats and doesn't give any utility for good 2. And under this circumstance, her utility goes from 1 to 2, 1.5 because both of them have preference for 1 over 2, the same amount of preference really, because, and each of them will get half of 1 and 2 each. So the utility of buyer 2 went up from 1 to 1.5, and this can be extended all the way to 2. So here's what we showed. Bottom line is the Nash bargaining based one-sided matching market is factor 2 incentive compatible and factor 2 envy-free both, and both factors are tight. Okay, so remember Nash. Hylland and Zeckhauser was incentive compatible in the large, which is a slightly meaningless thing because when do you have a market with arbitrarily many buyers of the same type and arbitrarily many goods of the same type? Okay. This is real incentive compatibility, but it's factor 2. It's apples and oranges, but that's what happens.
So what does factor 2 mean?
That means that, good question. So, incentive envy-freeness up to factor 2, that means that the allocation produced by this mechanism will be such that nobody will envy somebody else's allocation by more than factor 2. Okay. Under envy-freeness, you're not supposed to envy anybody else's allocation at all, but you don't envy any more than factor 2. So okay. And factor 2 incentive compatibility means that if I cheat, I cannot gain by more than a factor of 2. I misreport my utility. Normally, incentive compatibility says if I misreport my utility, I don't get anything better. Well, I could get something better, but not more than factor 2 better. Okay, and moreover, both these factors are tight. And then we also managed to prove a theorem that there is an incentive compatible and Pareto optimal and rational solution using polyhedral methods. And then comes the question: can it be found efficiently? Somehow, not through a mechanism, but even in polynomial time efficiently. There is such a solution. Can we find it? And the answer is no. We showed that finding such a solution is also PPAT hard by reducing approximate HC to this. And so that's the gap. So finding exactly NV-freeness and NV-free and Pareto optimal solution is PPAT hard. Finding factor 2 is polynomial time through and bargaining. So that's the gap between what cannot be achieved and what can be achieved. And the gap, in some sense, is small because it's just a matter of factor 2. Okay, so in some sense, the bottom line is that there may not be a much better alternative than the Nash bargaining test model. Certainly, there may not be a, let me put on the word much better. Okay, but between these two extremes of having a solution which cannot be found and a solution that can be found, there are many other possibilities. Right? You may be able to trade off factor 3 NV-freeness to 1.5 factor incentive compatibility, because maybe you care more for incentive compatibility than NV-freeness or something. So all of that is open. Like Daniel Sutter wanted open problems. There's a slew of open problems. What is this terrain between this possibility, which is PPAT hard, and this possibility, which is in P? What does just terrain look like? How much of it more can be captured in polynomial time? How much of it more is PPAT hard? I think there's a lot of work that needs to be done here.
Director que aí eu sou ali pegar todos os daí família bem tipo de alta férias put this in one direction to explore the spectrum, replacing the log by something more general.
Replace what by more general? So
the log replacing it by something more general would be one approach to
I mean, one has to be more creative and explore it in that spirit, I think. See what comes out. Okay, so, but that's as far as one-sided matching markets go, but that's not the end of the story. So more general than Fisher market is arrow-W market, and for the arrow-W extension of Hylland and Zeckhauser, Hylland and Zeckhauser themselves realize that the pricing mechanism does not work because there may not be even an equilibrium. So Kakutani doesn't extend to this model. And so no more work was done on matching markets beyond this. So only one-sided matching markets were studied, two-sided and other utility functions, more complex functions, nothing was studied. But using the Nash bargaining, all of these turn out to be doable. Okay, so it's two-sided, where you match employees to employers, and many different utility functions, linear, linear, concave, and so on. All of that can be done in the Fisher as well as the exchange settings. Okay. So Nash bargaining really gives a lot, and not only that, but non-bipartite matching markets where, say, you have the stable roommates problem, but you want to study it as a market where people give cardinal utilities for their possible roommates, and you want to find a maximum weight matching there. I mean, some a mechanism that matches students to students in a non-bipartite way. Even those market models can be done using Nash bargaining, and all of these markets were inspired by general equilibrium theory, which has a very rich collection of market models. for many different situations, natural situations. Okay, that's my talk.
Thank you. Any more questions?
Yeah.
The fact that you got me thinking about a problem that I don't know how realistic it is, but imagine a scenario where goods can be shared for about like up to n people. So instead of just one person getting one house, you can get like n people getting in this house. It seems like the factor would go down for two.
You think in practice, yeah. These worst case examples are really worst case. So in practice, this factor 2 will be much smaller.
But I'm talking about a different problem, right? Problem in which you can have a bunch of people sharing the same good.
Yeah. Oh.
Yes. So imagine.
So the good is
imagine on okay, this person gets this house, up to 2 people can get the same house, or 3 people, or like n people. So we have more people than we have goods, and we are matching.
But the goods are still indivisible.
Yes, the goods are still invisible, but they are shareable by the same.
Okay, that's a different kind of setup. Okay.
Yeah, and it seems like the factor would go down because you can like the reason why it's true from my understanding is that the worst case scenario is that somebody is not getting what he wants and like all his utility is going to the other person, but he gets double the utility, his own utility and the other guy's utility. But if we are sharing like this, maybe we can bring this factor down. Not sure if I agree, like if this makes sense, but just some like what the problem was thinking.
Yeah, no, it's worth exploring. It could be that the NB3-ness factor will go down. It could be, but you think it should be provably the case, right? Maybe that would be a very fine result. Yeah. Nice extension though. Yeah. I mean, these have been studied also by Hylland and Zeckhauser. Didn't only do one-to-one matching, but several people want the same good kind of thing also, or a person wants more than one good also. Yes.
More questions?
Yeah, maybe in line of this thought, as I understand, one mapping is between these matching which are one-to-one, which relate to kind of direct degree clusters and people are directly connected to each other. But I wonder if you have any thoughts on the indirect case that there may be matchings involving cycles, for instance, involving more entities that may eventually help each other in indirect ways.
So cycles, I'm not sure I follow that.
Well, maybe it's out of scope.
Maybe we talk later. Yeah, it seems like you have a bigger thought in mind. Let's talk later.
Okay, yeah.
Sounds I want to know what that is. Okay. And any other questions?
I actually have a question that might be a little bit related to one thing I was saying. I know it's kind of a little bit out of scope, but we were talking about one-sided matches. So what would it be like two-sided matches? Would it be like both sides have utilities?
Yeah, like employees to employers. So you have like firms and workers.
So you have to maximize it like both utilities.
Yeah. What you want to maximize, you have to decide.
Oh, okay.
But you have two utility functions.
Okay. I think maybe in this context, maybe what I was saying could happen, like influence both sides and create like.
So normally, stable matching of Gale Shapley is like that. It's two-sided, right? The workers have preference for firms, and firms have preference for workers. But those utilities are ordinal. Suppose you replace it by cardinal, so numbers. Then what happens? And what's the market there? And what are you maximizing? I mean, figure that out. So,
Okay.
so that we can do using Nash cognitive.
Okay. That's interesting.
Okay, so let's thank Vijay again for presentation. So as I mentioned, we're going to go for lunch here in Projectors, Block F, and in the afternoon, Vijay is going to be around. So if you want to catch up with him and discuss your work with him, you're certainly welcome. Just coordinate with me or Daniel Sadok. You're going to probably meet him in H-317, the room here, okay? All right.